If you ask any freshman science student, they could tell you this is a better picture of an atom than this. They both have positive protons and neutral neutrons in the middle in the nucleus, and they both have electrons around the outside. But in this case, the electrons are only allowed to go in certain places or rings or orbitals. And we spend a lot of time making students know that 2 fit in the first and 8 in the next and 8 in the next and so on. In this video, I want to discuss why that matters, why it's so important, and what evidence do we have for it. To start, we really need to understand that the distance an electron is from the nucleus is a measure of how much potential energy it has. The nucleus is positive, the electron's negative. They would tend to move together. So the farther away we move it, the more work we have to do, the more energy we give it. So this model here is a statement that the electron can have any potential energy I want it to. This model here is saying no, there's only certain places it's allowed to go. And that 2 of the electrons in, say, an oxygen atom have a different potential energy than the other 6. So if we were going to say that, we better have some evidence for it. And it's kind of amazing that we can, because atoms are so tiny and electrons dance around between energy levels so quickly. But it turns out we can measure the energy released or gained as electrons jump from level to level. And that's how we know this. So how do we do that? Well, imagine I couldn't measure potential energy of something like a textbook, but I could measure how fast the textbook goes when it hits the ground. Since potential energy gets converted into kinetic as the textbook falls, then all I'd have to do would be measure the speed of the textbook as it hits the ground, and I could backtrack and figure out its initial potential energy. You've learned that light corresponds to energy. And you've learned that different colors of light carry different amounts of energy because their photons each carry amount of energy equal to HF, Planck's constant times the frequency. If we look at an atom like hydrogen and we excite its electrons using electricity and allow them to fall from higher energy to lower energy levels, we get light. And that color of light might tell us a little bit about what's going on with those electrons. Just to figure out what's happening, we should probably check whether the light hydrogen gives off is one color of light or many. And we can do that by looking at hydrogen through a pair of diffraction grating glasses, which send different colors of light to different places. If you do that, you can see that hydrogen does consist of many colors of light. A red, a teal, and it's hard to see because it's bunched up, but a couple different purple ones. So why? The model that was come up with by the great Danish chemist Niels Bohr is that unlike a textbook falling where its potential energy becomes kinetic energy, an electron falling, its potential energy loss is turned into light. And his model is that, say, this red color we're seeing corresponds from electrons falling from the 3rd ring to the 2nd ring. That's going to be a loss of potential energy, and that's converted into this red light. The teal light, he thought, was electrons in the 4th ring falling to the 2nd ring. The first purple from the 5th ring to the 2nd, the second purple from the 6th ring to the 2nd. So by knowing how much energy gets lost as you jump from higher level to lower level, you can start to figure out how much energy those different levels have. First thing we need to know is how much energy do each of these photons carry. So the way we can do that is we can observe hydrogen through what's known as a spectroscope. So spectroscopes look like this black thing. And if you point the slit at a a source of light, it separates out the different colors along a scale. So this is me pointing this at an old incandescent light bulb, which gives off all the colors of the visible spectrum, which should range from about 390 to around 700. And we can see that it's pretty accurate. My eyes are not that sensitive to colors as we get closer to 400. They're there, but they're so dim I can't really see it. These are not very high quality. So what I typically do is have every student point their spectroscope at the hydrogen and record what they think the lines are. And I have them put in a spreadsheet what the values they observe are, and then we average them. Notice that no student saw a line that almost everybody agrees is there at 410 nanometers. I didn't see it either. But we all saw the other three. And on average, we're pretty close, but not identical to what the accepted values are. Interestingly enough, although I didn't even see that 410 nanometer light, my phone can when I take a picture of it. Again, it's just so dim, our eyes aren't as sensitive to it as we'd like it to be, but our phone electronics are. So it is something we can record if we look through the lens of a phone. So basically, we're going to say these different colors correspond to electrons losing energy as they jump from higher levels to lower levels. And the first thing we need to do in order to figure out how much energy is being gained or lost is we need to convert the wavelengths of light in nanometers. We need to convert it into an energy unit. The unit we're going to use for energy is called the electron volt. The joule is a very large amount of energy compared to the tiny amounts gained or lost as electrons move, so it's not very convenient. Electron volt sounds awkward. It's literally the charge on an electron times a volt, but that's coulombs times joules per coulomb, which would give us joules. So it really is an energy unit. We can convert wavelength into energy by using the Planck-Einstein relationship and the wave speed equation, remembering the speed of light is c, 3 times 10 to the 8 meters per second. Combining those two equations gives us this equation, which can convert our wavelengths into energies. Here's a sample calculation here. I'm using this value of Planck's constant, which uses electron volts instead of joules. It's your choice which one you use, but if you use this one, your units end up in electron volts. So each of these wavelengths of light corresponds to a certain energy transition. What I want to do is use the energy that we get when we say go from 3 to 2, which we've now calculated to be 1.893 electron volts. And the energy we've gone from 4 to 2, which is 2.556 electron volts. I want to use those transition energies to figure out the absolute energy of each level. So how do we do that? Well, the first thing we have to do is recognize that there are other possible electron jumps. And these lines here that we observe with our spectroscopes, Joseph Balmer, long before anyone knew what was going on inside the atom, he found an equation that fit these values. And basically the allowed wavelengths can be figured out with this equation where the inverse wavelength equals a constant times the difference of two fractions. And the fractions have square integers on the bottom. Balmer realized that you could plug any pair of integers in here you wanted and get lots of different values that corresponded to light outside of the visible range, but that the visible light we see always happens when one of these integers is 2. Niels Bohr realized that what that's saying is these are electrons falling from higher energy levels to the second energy level. So we need to know about a transition to the first energy level in order to make our chart of allowed values. So The lowest energy in the ultraviolet that we get is a photon corresponding to 121.6 nanometers, which is 10.214 electron volts. And that's to go from n equals 2 to n equals 1. N equals 3 to n equals 1 would be bigger. So once we know this difference and we know each of these differences, we should be able to start spacing these out and find out the absolute level of each energy level. The only other piece of the puzzle we need is a 0 point. What is the 0 point for energy? What is 0 electron volts? And when we talk about atoms, we say infinitely far away, an electron infinitely far away from the nucleus, or ionized, is the 0 point. You've seen something like that before. You pick a 0 point at infinity when you discuss how much energy an object has as it moves away from a planet. So this is different than how we talk about energy like in a classroom. If I have a ball on a floor, I would usually call that 0 potential energy, and I'd lift it to a certain height, I'd call that mgh. When you're talking about moving away from a planet, calling the surface of the planet 0 is difficult because it's really from the center of the planet we have to measure from. So every distance away from the center of the planet, whether it's inside the planet or outside the planet, is going to have a different potential energy. And it's easiest to just call as far away as possible where the force of gravity has dropped off to call that potential energy 0. And to say anything closer than infinitely far away has a negative potential energy. It's awkward. It means that all real potential energies are negative, and that the closer we get, the potential energy gets more negative. But it's totally valid. You're allowed to pick any 0 point for potential energy you want. If I'm in an upstairs classroom dropping a ball, from my perspective, from 3 meters high to 2 meters high, that's going to cause a certain change in potential energy. And it's going to correspond to a loss of 5.39 joules. If I called the ground 0 meters, and instead of thinking of the ball as falling from 3 to 2, but instead from 7 to 6, it's still going to cause an energy loss of 5.39 joules. What I pick as my 0 doesn't matter. So since figuring out the energy required to ionize an electron is relatively easy, we call the electron being ionized infinitely far away. We call that energy 0. The ionization energy of the ground state of the hydrogen atom is 13.6 electron volts. So we're going to call n equals 1, 13.6 electron volts. So how do we build our absolute level, our absolute model of how much energy each of these rings has? If n equals 1 is minus 13.6 electron volts, the energy of the photon to go from 2 to 1, 10.24 electron volts, we just add those two together and we get minus 3.36 electron volts. That's n equals 2. You want to figure out n equals 3? Take your 3.36 electron volts and add that red hydrogen line that we see, 1.89 electron volts. That gets you n equals 3. Add the teal line, 2.556, add that to n equals 2. That gets you n equals 4. So you basically can build up your absolute energy level just by knowing your ground state and then how much energy is required to transition to each of the other states. And the photons tell us that. So here's the overall model you build. You could see why going to the ground state releases a lot more energy per photon. In other words, ultraviolet photons, because it's actually, there's a much bigger energy gap between n equals 2 and n equals 1 than there is between the others. Increasingly larger values of n are closer together in energy. Once you build this absolute spectrum, you can use it to make predictions. If you wanted to find all the other transitions that we haven't talked about, you could just figure out how different the two levels are on our diagram, figure out the energy difference in electron volts, convert that to nanometers, and you'll now know the color of light that's emitted when an electron jumps from a higher level to a lower level, any of them. So this altogether is the Bohr model of the hydrogen atom. And ultimately it tells us there are certain places electrons can go and the energy that each of those places have when you put an electron in them. Interestingly enough, other atoms have different electronic transitions. This is helium. This is neon. This is argon. And if you try to use this formula in this model for anything other than hydrogen, it doesn't work. Having a multi-electron atom makes it too complicated and shifts the levels. So we've had to improve on the Bohr model ever since in order to explain other atoms. But it's still worth learning this because at the end of the day, this explains to us what's happening as electrons move around inside an atom. And it's a good first step to understanding more complicated atoms, which you'll learn about in a later class. So what I'd like you to do, if you're watching this video, probably didn't see the lab or participate in the lab. What you're going to need to do is basically take our data we had for the hydrogen atom, convert these into electron volts, know that the ground state is 13.6, and go ahead and build on graph paper your scale model of what the allowed energy levels are for hydrogen.